In the previous lectures, we have been talking about depth first search, we have been talking about the implementations either with iteration and with recursion. In this lecture, we are going to talk about the applications of depth first search. So first of all, we can use depth first search for pathfinding algorithms. So artificial intelligence and machine learning approaches help robots discover the surrounding easily, either with breadth first search or with depth first search. Then of course we can use depth first search in order to find the topological ordering that has several applications. For example, in build tools such as Maven or Gradle, the topological order of the processes are extremely crucial. And by the way, we can find the strongly connected components with the help of topological ordering. Okay, so the next application has something to do with strongly connected components. So with the help of depth first search and topological ordering, we can find strongly connected components of a graph that has several applications again. For example, we can state that the items within a strongly connected component are quite similar to each other. So for example, this is how we can suggest similar videos to users on YouTube. And by the way, these kinds of strongly connected components have been used, of course, with the advent of deep learning. YouTube uses machine learning and deep neural networks in order to suggest new videos. But of course, strongly connected components remain quite useful. Of course, we can do the same with social media such as Facebook or Instagram, because of course the users belonging to the same strongly connected component may share several friends. So usually Facebook suggests the users within the same strongly connected component for people you may know. So these are the suggested friends. Okay, so that's all about strongly connected components. And of course, finally, there is the cycle detection problem that is again extremely crucial, and we can use depth first search in order to detect these kinds of cycles in an underlying directed graph. And it is absolutely crucial in operating systems. I'm not sure whether you are familiar with processes, but essentially every single operating system runs the so-called processes. And of course, these processes may wait for each other, and we would like to avoid so-called deadlocks when these processes are waiting for each other to finish execution and they are not able to be executed because of this. And of course, we can construct a directed graph out of these processes. The vertices are the processes themselves, and of course, the relationships are the edges. And of course, the aim is to avoid cycles in this graph. Anyways, I don't want to get into the details of operating systems, but these kinds of graph algorithms have several applications. Thanks for watching.